Hi everyone, thrilled to have you back with us here at educator.com. Today we're going to start a lesson on electric fields and forces, which is the beginning of our unit on electricity and magnetism. Our objectives are going to be to calculate the charge on an object and explain the law of conservation of charge, describe differences between conductors and insulators, explain the difference between conduction and induction, use Coulomb's law to solve for the force on a charged particle due to other point charges, calculate the electric field due to one or more point charges, and finally to analyze electric field diagrams. So let's start by talking about electric charges. As you know, matter is made up of atoms, and those atoms even have smaller particles, subatomic particles, such as protons, electrons, and neutrons. Now, protons have a charge of +1, and +1e is a +1 elementary charge, the smallest stable single charge. That's equal to 1.6 times 10 to the minus 19 coulombs, the SI unit of charge. Electrons, on the other hand, have a charge of -1 elementary charge, and neutrons are neutral. Now, most atoms are neutral. They have equal numbers of protons and electrons. The positives and the negatives balance out for a net charge of 0. It's neutral. But if an atom loses its electrons, loses an electron or two, it's going to become positively charged. Or if it gains an electron or two, it's going to become negatively charged. We call those charged atoms ions. Now, the fundamental unit of charge in the SI system is the coulomb, capital C. And that's for a big All right, as we talk about materials, conductors are materials that allow charges to move freely. They have a very low resistivity. Charges can go through them very, very easily. Insulators, on the other hand, don't allow charges to move freely. They have what's known as a very high resistivity. And resistivity is a material property. If you look up the resistivity of gold, it has a certain value. If you look up the resistivity of glass, it has a specific value. It's a material property measured in ohm meters. And it typically gets the symbol rho, a squirrely little p. All right. Materials may be charged by contact, known as conduction. And you might have tried this trick before. Rub a balloon against your hair someday. Some electrons from the atoms in your hair get transferred to the balloon. The balloon now has a net negative charge, and your hair, because it lost some electrons, now has a net positive charge. You can also charge conductors by contact. For example, if you bring a charged conductor into contact with an identical neutral conductor, you will share the charge across those two conductors. Let's take a look and see how that would work. A conductor carrying a net charge of 8 elementary charges is brought into contact with an identical conductor with no net charge. When they're brought into contact, because they're conductors and charges can move freely, those charges, those 8e, they're all positive. That's a positive charge. They're going to repel. They want to get as far apart from each other as they can. So what do? They split up, so you get 4e on each conductor. If those conductors are identical, you get the exact same charge on each. Then if you split them apart, you now have 4 elementary charges on each object. So what would the charge be? 4e on each one is going to be 4 times the charge on an elementary charge, 1.6 times 10 to the minus 19 coulombs, which is 6.4 times 10 to the minus 19 coulombs. Now on a conductor, the charge is always going to sit on the outside surface. So the electric field inside a conductor, as we talk about fields here soon, is always going to be 0. Something to remember, electric field inside a conductor is 0. Let's talk about the electroscope. The electroscope is a really cool tool that's used to detect small electric charges based on conduction. It consists of a conducting rod in a beaker that is then insulated from the outside world except for this metal knob that sticks out the top. If you were to bring something like a positively charged rod over to it to share the charge, you're going to get a net positive charge on your metal rod, and as that's distributed throughout the rod, at the bottom you have these 2 very thin leaves. If you have positive charges on each of the leaves, they're going to repel, and you get a spreading of the leaves. It indicates that you have a charge. You could have the same basic thing happen if you were trying to do this with a negative charge. If we draw just the metal part of our electroscope here, and we bring a negatively charged rod near it, well, now the electrons that are already on that metal rod, without even touching, they're going to be repelled from the negative charge there, and they're going to try and hang out as far away as possible from that negative charge, leaving this end positive. Well, once again, down here on those leaves, you have negative charges on each leaves. They'll repel. So this is really a charge detector. You could also charge by induction. That's charging a conductor without actually coming into contact with another charged object. So if we start off with a neutral electroscope here and bring a positive rod near it, we'll have the electrons all want to gather near the positive charge, opposites attract, leaving a net positive charge down near the leaves of the electroscope. They'll spread apart. Now what we're going to do, though, is while we hold that rod in place, we're going to connect this metal bar to ground. And by some connection to ground to the earth through a conductor, the earth acts as an infinite sink or source of electrons. If you need some electrons to balance things out, you can pull them straight from the earth. You've got tons of extras. If you need to get rid of some, you can throw them into the earth very easily. So now when you connect this to ground, it sees all the positive charges here, and you'll start sucking some electrons up from the ground in order to make that balance nice and happy. Now, if you disconnect the ground connection, those charges are stuck on the metal conductor. You have a net negative charge on the electroscope. And of course, down here where you once again have negative charges on the leaves, the like charges repel each other and you see the spreading of the scope. You have therefore charged the electroscope by induction. You haven't touched it specifically to the source of charges, to that glass rod. Let's talk about electrostatic attraction. A positively charged glass rod attracts object X. What can you say about the net charge of object X? Well, before we can answer that, let's think about what could happen here. If we have a positively charged glass rod, it's pretty easy to see that if you have some other negatively charged object, that it will attract. So, without a doubt, you could say that you could attract a negatively charged object. That's easy. But what if the object's neutral? Well, if it's a conductor and it's a neutral object, you'll actually have some of the electrons in the object will want to hang out over near the positive charge. It remains electrically neutral, but because you have a negative closer to the positive than the positive positive, you have a net attractive force, so you can actually attract neutral objects. What, on the other hand, would happen if you had that positive rod, and instead of a conducting sphere like we had there, let's talk about an insulating sphere. Well, the atoms actually in this insulating sphere are made up of a positive nucleus and a negative electron orbiting it, or multiples. When you bring the positive charge near it, the electrons are going to want to be attracted to that positive rod. They'll want to spend just a little bit more time in their orbits over toward that positive rod side. So you're going to actually get the atoms or molecules to polarize just a little bit, the ones at the edge, and as they do that, you have a slight attractive force that's stronger between the positive and negative than the repulsive force from the positive to the positive. You've created a slight polarization of those molecules electrically, and you can attract a neutral insulator that way as well. So what's the answer? The net charge of object X, it could be neutral, or it could be negative to get attracted. Same thing would happen if you had a negative glass rod. It could attract something that was either positive or neutral. Now, the only way to prove that two objects are charged is by repulsion. You can attract neutral objects with one charged object. You can't repel unless both objects are charged. Let's talk about Coulomb's law as we try and quantify this electrical force of attraction or repulsion. As we know, like charged objects repel and opposites attract. Charged objects, therefore, must apply a force upon each other. That's known as the electrostatic force or the Coulombic force. And similar to gravity, the force of attraction or repulsion is determined by the amount of charge instead of mass and the distance between the charges. So the electric force is equal to some constant, K, that's called the electrostatic constant. It has the value 9 times 10 to the 9th Newton meters squared per Coulomb squared, times the charge on the first object, times the charge on the second object, divided by the square of the distance between them. It's another inverse square law. And notice how similar that is to the force equation we had for gravity. Universal gravitation, the gravitational force was G, m1, m2 over r squared. Notice what we have here. Instead of K, we had G for gravity. Instead of charge, we have masses. And distance between their centers? Distance between their centers. It's almost the same thing, just in a different regime. The biggest difference is that gravity can't repel, while the electrostatic force can attract or repel. So, determining the electrostatic force. 3 protons are separated from a single electron by a distance of 1 micron, or 1 times 10 to the minus 6 meters. Find the electrostatic force between them. Is that attractive or repulsive? Well, let's answer the easy question first. If we've got protons, 3 protons, that's going to be a charge of plus 3 elementary charges. The electron will be minus 1 elementary charge. Opposite charges are going to attract. Now, however, let's find the force between them. Let's call our protons our first charge, Q1. So that's going to be 3e, or 3 times positive 1. happen to our electron beam. If these are negative charges, they're going to get attracted by this side, so we're going to have a force that way to do attraction here, and they're going to be repelled by the negatives here, so we'll have a force that way. So our net force, both of these are going up, is going to deflect it up. So we have a net force upwards. Okay, electric fields. The electrostatic force, just like the gravitational force, is a non-contact or field force. We can't see it. The way we can detect it is by placing a charge somewhere in space and then seeing what force it has acting upon it. The property of space that allows a charged object to feel a force is what we call the electric field, that mental construct to help us understand what's going on. You detect the presence of an electric field by placing a positive test charge at various points in space and measuring the force the test charge feels. What that means is the electric field is always going to point in the direction of the force on a positive charge, not on a negative charge. The electric field points the direction of a force on a positive charge. We quantify this with the electric field strength vector, capital E, and that's the amount of electrostatic force observed by a charge per unit of charge. So the electric field strength, E, is the electric force divided by the amount of charge. It's the force per unit charge. Its units are going to be, well, force is newtons, Q, charge is in coulombs, so that's newtons per coulomb, and we'll later find out that that's equivalent to volts per meter. Newtons per coulomb or volts per meter, same thing. And again, the direction of the electric field vector is in the direction a positive charge would feel a force. So let's take a look at another example. Finding the field between some metal plates. Two oppositely charged parallel metal plates, 1 centimeter apart, exert a force of 3.6 times 10 to the minus 15 newtons on an electron placed between the plates. Calculate the magnitude of the electric field strength between the plates. Well, let's write down what we know so far. First off, our parallel plates are 1 centimeter apart, so the distance between our plates is 0.01 meters. There is a force, an electric force, of 3.6 times 10 to the minus 15 newtons on an electron. What do we know about an electron? Its charge is negative 1e, or negative 1.6 times 10 to the minus 19 coulombs. We want the magnitude of the electric field strength, so we're looking for capital E. Well, from our definition, the electric field strength is the electric force divided by the charge, which is 3.6 times 10 to the minus 15 newtons over negative 1.6 times 10 to the minus 19 coulombs, which gives me an electric field electric force follows an inverse square law relationship. Around a negative charge, you also have this radial pattern, but now the field lines point in. The lines point away from positive charges and into negative charges. Now down here, I have a couple of dipoles, two charges near each other. If we find the electric field, what we're going to do is vector addition of the individual fields. But if you have a positive and a negative beside each other, well, electric field lines go from positive to negative charges. So we're going to get a pattern that looks kind of like this. And you could fill in more lines if you wanted to as you interpolate between them. And so on. The key, they go from positive to negative, they never cross, and they show the direction of the force on a positive test charge. If I were to go take and put a positive charge right there in space, pretty easy to see that the net force it's going to feel is probably going to be somewhere in that direction. If I were to go take a positive charge and put it right there, that yellow positive charge is going to feel a force to the right toward that negative charge. The electric field line is telling you the direction of the force on a positive test charge. Now over here on the right, bottom right, we have two positive charges making a dipole. Well, electric field lines go away from positive charges and they don't cross, so you end up with a pattern that looks kind of like this. And what's interesting here is if you were to take a positive test charge and put it exactly in the middle of those two, the forces on it are going to balance out so you get a net force of 0. Right in the middle, you've actually got a dead spot while you're exactly at that point. So, a little help to get you going on visualizing electric field lines. Let's talk about calculating the electric field due to a point charge. Electric fields are caused by charges. The electric field due to a point charge can be derived from what we know about the electric field and Coulomb's law. We already know the electric field strength is the force divided by the charge, and Coulomb's law says that the force of the electric force on two charged objects is this constant K times the product of the charges divided by the square of the distance between them. We can put those together to find a definition, a formula for the electric field due to a point charge. If the electric field strength is force divided by charge, and force is K Q1 Q2 over R squared, and I still have this Q in the denominator there, well, we can cancel out or make a ratio of 1 from one of our sets of charges, and we find that the electric field strength is KQ over R squared. That is the formula for the electric field due to a point charge. To find the electric field due to multiple point charges, take the vector sum of the electric fields due to each of the individual point charges. You just keep adding them up in vector fashion. So let's take a look at comparing electricity to gravity again. There are so many similarities. Force is F kq1 q2 over r squared for electricity. For gravity, it's g m1 m2 over r squared. We've swapped the k for g and the q for m, charge for mass. Same basic pattern though. The field strength, electric field strength, is the electric force divided by the charge. The gravitational field strength, little g, was the gravitational force divided by the mass. Again, a nice parallel. The field strength due to a point charge was kq over r squared. For gravity, that was gm over r squared. Same parallel. Now they have different constants, and notice k here on the left is 8.99 times 10 to the 9th. I tend to just make that a nice simple 9 times 10 to the 9th. So if you see that written differently somewhere, don't worry, it's close enough. On the right side, the gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Again, these are really just fudge factors to make the units work out. And the charge units were coulombs, the mass units, kilograms. Lots of parallels. So let's take a look at a little bit more in-depth problem solving. Find the electric field at the origin due to the three charges shown in the diagram. We've got a plus 2 Coulomb charge here at 0, 8, a plus 1 Coulomb charge here at 2, 2, and a minus 2 Coulomb charge here at 8, 0. Well, what we're going to do, our strategy is going to be to find the electric field at the origin to each of the individual charges and then add those up in vector fashion. So let's start by looking at our green charge up here at 0, 8. If that's a plus 2 charge, the electric field is going to point away from it, so we're going to have the electric field going in all these directions. And at the origin, that must be pointing down. So right away, we know that we only have to worry about the y component. Now the electric field strength is kq over r squared, where K is 9 times 10 to the ninth, our Q is 2 coulombs, and the distance from the origin to our charge is 8 meters. So that's going to be over 8 squared, or 2.81 times 10 to the 8th newtons per coulomb down. And if I want to write that in bracket notation, my x component is 0. My y component is going to be negative 2.81 times 10 to the 8th newtons per coulomb, because we know that must be pointing down. So there's the electric field due to our green charge. Let's do the red charge next. The electric field due to that red charge is again kq over r squared, where k is 9 times 10 to the ninth, q is negative 2 coulombs, but again, we're not going to worry about signs at the moment. Let's get the magnitude, and we'll use common sense to figure out its direction. And its distance, 8 units from the origin. 8 squared is going to give us the exact same thing. 2.81 times 10 to the 8th newtons per coulomb is the magnitude. But if this is a negative charge, electric field lines point into negative charges. So from the origin, we must be going toward the right due to that negative 2 coulomb charge. So this would be 2.81 times 10 to the 8th newtons per coulomb toward the right, or in the positive x direction. So in bracket notation, I'm going to write that as 2.81 times 10 to the 8th newtons per coulomb, and it has no y component. So we have the electric field due to the green charge, the electric field due to our red charge. Now let's see what it is due to our blue charge. If this is plus 1 coulomb, it should be pretty obvious to see that the electric field at the origin will be pointing away from it, that direction. So we'll have components in the negative x and the negative y direction here. Let's find its magnitude. E equals kq over r squared, which is 9 times 10 to the ninth. Our charge is 1 coulomb, and now we've got to get the distance from the origin to that charge. Well, to do that, I'm going to make a right triangle here, and if that's 2 units and that's 2 units, then by the Pythagorean theorem, this must be the square root of 2 squared plus 2 squared. So that's going to be over square root of 2 squared plus 2 squared squared, or 9 times 10 to the ninth over 8, which is about 1.13 times 10 to the ninth newtons per coulomb, but that's going to be down and to the left at an angle of 45 degrees because it has equal x and y components, which we can see just from the symmetry of the situation. So that means if I want to break this into x and y components, this is going to be equal to, well, we're going to have its magnitude, 1.13 times 10 to the ninth newtons per coulomb, and the x component will multiply by the cosine of 45 degrees, and I know that's going to be negative. And for the y, it's also going to be negative 1.13 times 10 to the ninth times the sine of 45 degrees, the y component, and those are going to be the same. Sine 45, cosine 45 is the same thing. When I run that through my calculator, I find that that's going to be about negative 7.95 times 10 to the 8th for the x, and negative 7.95 times 10 to the 8th for the y, all in newtons per coulomb. So now I want the total charge, the total electric field at the origin due to those three. So the total, all I'm going to do is I'm going to add up the x components and add up the y components. So my x components, I have 0 from the green charge. I have plus 2.81 times 10 to the 8th from the red charge. And I have negative 7.95 times 10 to the 8th from my blue charge. So that's the x component. The y component, I have negative 2.81 times 10 to the 8th from the green, plus 0 from the red, and minus 7.95 times 10 to the 8th from the blue. And again, all of that's newtons per coulomb. So I pull out my calculator, I add up all my x's, add up all my y's, and I end up with a total electric field of about negative 5.14 times 10 to the 8th for the x, and negative 1.08 times 10 to the 9th for the y. And all of that is in newtons per coulomb. So a little bit more math here to get through it, but really the same basic concept. Find the electric field due to each of those points, and then sum them up to get the total electric field over here at the origin, which is going to be, we have a component to the left, we have a component that is down, so we're going to have something where we've got a net electric field down in that sort of southwestern quadrant, quadrant 3 of the graph. All right, let's take a look at another problem. Determine the x-coordinate here on this line where the electric field is 0 using the diagram below. And we've got a plus 2 coulomb charge here on the right and then plus 1 coulomb charge here on the left. Going to follow the same strategy again. Let's take a look at the electric field due to that blue charge. We'll call that E1. That will be KQ1 over R squared. Well, when we do this, let's try and figure out roughly where our answer is going to be. As I look down here, if I've got a plus 1 coulomb charge to the right, that's going to give me an electric field to the right. Plus 2 coulombs over here to the left is going to give me an electric field to the left. And because plus 2 is stronger, I'd expect that my 0 point is probably going to be somewhere a little closer to the plus 1 charge than it is to the plus 2 charge. So I'm going to make a guess and say that we're probably going to be somewhere over in that sort of region. All right, if we call this distance between our plus 1 coulomb charge there at negative 6 and our point R, then that means that over here, this distance must be 11 minus R. So if I want to draw the electric field due to E2, due to this red charge, we'll call that E2 is KQ2 over, and our distance now will be 11 minus R squared. And we want to find out the point where those two, where the net electric field is 0. So where those are going to be exactly equal in magnitude. So our total electric field is going to be, well, we have our blue one, our blue electric field over here. K times Q1 is 1 coulomb divided by R squared, and we'll have to subtract, because this is going to the left, the electric field due to the red charge. So that will be minus K, the charge is 2, divided by 11 minus R squared. And we want the point where that all is equal to 0. So first thing I can do here is I look at my problem is I see a simplification right away. We can divide K out of all of that. So I could rewrite this then as, let's see, 1 over R squared. I'll move the red part to the right-hand side, is going to be equal to 2 over, well, 11 minus R quantity squared. Let's extend that out. That'll be 121 minus 11R, which is minus 22R, plus R squared. So now a little bit of math here. If I multiply both sides, by R squared on the left-hand side, I'm going to get 1 is equal to 2R squared over 121 minus 22R plus R squared. Or with some cross multiplication, 2R squared equals 121 minus 22R plus R squared. Starting to look like a quadratic equation, so let's get it in that form. This implies then that 2R squared minus R squared plus 22R minus 121 equals 0. Now we can apply our quadratic formula. Some of you have calculators that may do that automatically, or you can go through the work there. And what I find is that I get a value for R of 4.56. It means if this is 4.56, then this distance, 11 minus R, must be 11 minus 4.56, which is equal to 6.44. So determine the x-coordinate where the electric field is 0 using the diagram below. So if we want the x-coordinate, well, now I just need to go back and finish this problem up to get the x-coordinate. That's going to be, well, if we start here at -6 and we add this distance r to it, 4.56, I get an x-coordinate of about -1.44. So it looks to me like our actual point for the correct answer should be at about -1.44, right about there. And we'll make our guesstimate go away. So we have found the x-coordinate where the electric field is 0. All right, let's take a look at an example where we look at gravity and electricity. A distance of 1 meter separates the centers of two small charged spheres. The spheres exert gravitational force Fg and electrostatic force Fe on each other. If the distance between the sphere's centers is increased to 3 meters, so we're tripling the distance, the gravitational force and electrostatic force, respectively, may be represented as. This is an inverse square law problem again. We have tripled the distance. Because distance is squared, we're going to have a change by a factor of 9. Now, is that going to be 9 times greater force or 1/9 the force? Well, we're going to have a smaller force because they're getting further away. So, because they're both inverse square laws, our correct answer must be A. 1/9 the gravitational force and 1/9 the electric force. All right, last problem here. In the diagram below, P is a point near a sphere that has a charge of -2 coulombs. What's the direction of the electric field at point P? Well, the way I would start this sort of problem is if we have a negative charge, let's draw some electric field lines. Electric field lines point in to negative charges. Well, this line is just going to keep going, so it looks like over here at point P, we would have an electric field pointing that direction. So the direction of the electric field at point P would be to the left, as shown right there. All right, hopefully that gets you a good start on electric fields and forces. Thank you so much for your time. Look forward to talking to you soon. Make it a great day, everyone.